Alright, welcome back to CSE 215, Lecture 3B. And in this lecture we're going to talk about functions. And we're familiar with the idea of a function from math courses, right? We think of something like y equals x squared or r equals the cosine of t. And we understand functions in this sort of intuitive sense, but we can actually define the idea of a function very precisely using what we've talked about so far in set theory. So let me give you an example here. Suppose we have a function f from a to b. So a and b are sets. They could be finite, they could be infinite, they could even be empty, but they're some sort of sets. And this is our notation for saying f is a function from a to b. Okay, what does this mean? For any a, which is an element of set big A, f of a is an element of b. So this function f is basically a mapping from elements of a to elements of b. And you can take any element of a, and by applying this function f, you get an element of b, which we call f of whatever that element is. So it's a notion of set operations, right? It takes elements of this set and it changes them into elements of this set. And pictorially, we could think of something like this. Here's our set A, here's our set B. For every point in this set A, f maps that point to something in B. That's all we need for f to be a function. But we have the usual requirements, which is that this point maps to exactly one point in B. We don't allow this point to also be mapped to another point. Okay, f is well defined. Given any element A, it takes you to exactly one point in B. Now, is it possible that 2 points map to the same thing? Absolutely. That does not stop it from being a function. All we require for a function is that for any point here, f maps you to a point here. Well, this point is mapped to something in B. This point is mapped to something in B. This is a function. Okay. All right. So an interesting observation is that we can think of a function as a set. It's the set of tuples where the first element is some element A belonging to set A, and the second element is the corresponding point f of A belonging to B. So it's the set of all pairs, ordered pairs, A comma f of A, such that A is contained in the set A. And here's the really cool part. This is a subset of A cross B. So think about that for a moment. Any function that we define going from A to B can be represented as a particular collection of these tuples which come from the set A cross B. So if we think of our universe as being the real numbers, and we think of f in our usual sense of f of x equals x squared, then this collection of tuples which corresponds to f would be something like 0, 0, 1, 1, 2, 4, 3, 9, along with the negatives, negative 12, 144, and the fractional ones, 0.5, 0.25, and so on. And this whole thing is a subset. Since f of x equals x squared, we're assuming this example goes from real numbers to real numbers. This whole thing is just a subset of r cross r. What does that mean? This one set, right? This is a set. It's a set of ordered tuples. This one set contains every function of real numbers. Sines, cosines, squares, logarithms, square roots, cubes, arbitrary functions, hyperbolic inverse cosines, whatever. All those functions are contained inside this one set. So this is really powerful, right? This is a simple to describe set, R cross R, that contains a set corresponding to each possible function from the real numbers to the real numbers. So that gives you some idea of sort of the power of being able to abstract things like sets, because it really captures some much broader concepts of arithmetic and mathematics. All right, so when we write a function f goes from a to b, we have some terminology. This set A that we're mapping from, this is called the domain. And this set B that we're mapping to is called the codomain. And if we look at all the elements in A, so let's say suppose A contains exactly 4 elements, and it maps therefore to some number of points here. And again, these could map to the same point, that's okay. But as long as each of these points is contained in B, B is a codomain for this function. But if we look at the set consisting of just these 3 points, that's something called the image. Okay, so the image is basically, it's the set of points that we map to using this function. Okay, and this is sometimes called a range, but I'll avoid talking about, I'll avoid the term range because it's not entirely well defined. But the image of a point is the thing that it maps to, and so the image of the entire set A is the collection of points that you map to when you apply f to everything in this set A. Okay, so what does it mean for two functions to be equal? Basically means they have the same domain, the same codomain, and they each map points to the same values. So saying f of 1 equals f2 means f1 of A equals f2 of A. Here's our symbol for all A contained in the set A. And it means, you know, that f1 and f2 both go from the same domain to the same codomain, so that this definition makes sense. So functions are identical when they basically map identical points to identical points. All right, so we'll experiment with some functions in class, and we'll see some functions that we're familiar with, and we'll see some sort of pathological functions that we may not have encountered. But this is interesting down here, what's going on. We're talking about equality of functions. Now, we normally talk about equality of numbers, and we can talk about equality of variables. We can say x equals y, but now we're talking about equality of functions. And why stop there? If we have two functions, f1 and f2, not only can we say, are these equal to each other, are these different from each other, but we can do operations on these. So given f1 from a set A to B, and another function f2 from A to B, we can define a new function which we call f1 plus f2, and this is also a function from A to B, and the behavior is f1 plus f2 of some point A is just equal to f1 of A plus f2 of A. And we're assuming that there's a notion of addition here, so for the sake of simplicity, let's assume that A and B are both a set of real numbers, so that this idea of adding things makes sense. So if we have two functions, we can express the sum of those functions, and we get a new function. It maps from things in A to things in B, or from reals to reals. And we can also define multiplication. So here's yet another function, f1 times f2, and it takes an element A and it maps it to f1 of A times f2 of A. So we can start doing arithmetic on functions, not just on numbers, not just on symbols, but on actual mathematical functions. And in fact, we can take this really far and we can start doing calculus on functions. We can get into something called functional analysis. And it's basically calculus, epsilons, deltas, derivatives, things like that. But instead of being applied to real numbers, it's actually applied to mathematical functions. And these functions can be simply mappings from one set to another. So this is an idea that's called abstraction. And abstraction is basically taking a concept that we understand in a particular setting and generalizing it to a general setting, right? And this is the basis of mathematical development, right? Here's one writing instrument, here's a second writing instrument. If I look at the collection, I have two writing instruments, okay? Here's one finger, here's another finger. If I look at them together, I have two fingers. But to make the leap from there to saying if I have one of something and I have another one of something, together I have two of that something, that's where we've actually made the leap to 1 plus 1 equals 2. Not 1 pen plus 1 pen equals 2 pens, or 1 finger plus 1 finger equals 2 fingers, but this abstract notion 1 plus 1 equals 2. And this is where the power of mathematics comes from, in some sense, is the fact that we can abstract specific experiences into these generalized ideas. That's a whole nother course, but it's worth mentioning at this point. Okay, so a few other aspects of functions. There's an identity function, which we can just write as I sub a. This is an identity function, and identity is always mapped from some set to itself. And it does something very simple. IA of x is just equal to x. And this is for any element x contained in A. So it's a well-defined function. It takes each element here and maps it to an element in the same set by taking an element and mapping it to itself. So it's kind of a boring function, but it's useful. Okay, we can also define an inverse function in some cases. So given f mapping from A to B, if f of A equals B, define a new function f inverse, and this is not a reciprocal, this is a new function f inverse, which takes B to the element A. So it basically reverses the arrows. But this is not always defined. And we'll see some examples in our homework as to why this may or may not actually exist. But if it exists, the property is that if f takes A to B, f inverse takes B back to A. Okay, we can also compose functions as follows. If f takes A into B, and g takes B into C, then we can write the following. We write g with a little circle f, and this is g composed with f. And this is a function from A to C. So to understand what this function does, we have to say what it does to each element of A. Well, g composed f applied to an element A is equal to g of f of A. Does this make sense? Yes, f of A is an element of B, and g takes elements of B to elements of C, so this will be an element of C. So g composed f is a function that maps from A to C. Again, we're going to go through examples of all of these things. This is going to help clarify some of these concepts. I'm giving you the basic ideas right now. All right, one more function I want to mention. Well, a pair of functions. These are called floor and ceiling. And we'll have use for these in a few weeks. So we write this with a different notation. This is a function applied to x. Okay, and for all of this, we're going to say x is some sort of real number. So this is called the floor of x, and this is the greatest integer, which is less than or equal to x. And if we write things like this, this is the ceiling of x, and this is the smallest integer, which is bigger than or equal to x. So for example, the floor of 2.1 is the greatest integer less than or equal to 2.1. Well, that's 2. And the floor of 2.0 is also 2. And the floor of 2.99999 is also 2, right? Greatest integer less than this. but the floor of 3 is 3 because that's the greatest integer less than or equal to 3. So it's kind of like a rounding function, but it has a precise meaning when x is negative. Alright, so that's enough about functions. We still need to talk about sequences and summations and matrices, and so this will be the topic of the last set of lectures for this chapter.